Our next series of videos, we're going to be taking a look at a field of chemistry called kinetics. Kinetics addresses two things. It studies how a reaction occurs, so by that we talk about mechanisms, and it talks about how fast a reaction occurs, which would refer to rates. When we talk about reaction rates, in the working world, and in particularly in business, time is money. Companies want to get the maximum output in as little time as possible. When it comes to the manufacturing of chemicals, plastics, pharmaceuticals, etc., the speed of a reaction has a huge impact on how much money that company can earn. Not only are reaction speeds important in earning money, but they also play a role in plant safety. Reactions that occur too rapidly can be dangerous, leading to potential explosions. Being able to control those speeds becomes vital. To control these speeds, we must understand what influences them. When we talk about reaction rates, we're talking about how fast the reaction occurs. Some may occur very slowly, taking millions of years, while others may occur very rapidly. Now, as we talk about things that are going to impact rates, we need to understand the requirements for a reaction to occur. And when we talk about those requirements, this is what we're going to refer to as collision theory. So in order for a chemical reaction to occur, reactant particles must collide, and they must do so with enough energy to break their original bonds. They also have to do so in the appropriate orientation. But right now we're just going to focus on the first two, particles colliding and colliding with enough energy to break their original bonds. And so we're going to take a look at a couple of scenarios so that we can walk through the factors that are going to impact our reaction rates. So looking at our first scenario, we have two containers housing the same reactants, A and B. The particles will be in constant motion, moving around the container randomly. We will assume that they are at the same temperature and therefore have the same energy. So looking at our first problem, we're asked which of these two containers should experience the most particle collisions. And looking at the difference in the containers, they differ by the number of particles. If we have more particles, we should have more collisions. So it should be container 2. So you think about if people can be spread out, they're less likely to bump into one another. So if you're in an elevator and you've got only 2 people, you can be on opposite sides of the elevator. You're not going to necessarily be bumping into one another. But you cram 10 or 15 people into that elevator in the same amount of space, you've got more people. More people are going to be more likely to have to come into contact. And so the same is true with our chemical reactions. The more particles here, the more likely they are to have more collisions. Based on that, we're asked which of the two containers do we think would have the fastest rate? So we just said that in order for a reaction to occur, our particles have to collide. If we have a scenario where we're getting more collisions, that means we're more likely to have reactions occurring, and therefore our rates will potentially be faster. So that is going to be container 2. And that is because more particles result in more collisions. So now let's think of this in terms of something we might do in the lab. So say we have a flask containing 50 milliliters of 0.25 molar glucose. I have another flask with 50 milliliters of 0.5 glucose. We're asked which flask has more particles. So same volume, 0.25 molar versus 0.5 molar. We would expect the 0.5 molar flask to have more particles. Remember that our molarity is moles of glucose per liter of solution. And remember that moles count our number of particles. So larger moles mean more particles. Say that in lab you have flask A, in which there's 100 milliliters of 0.1 molar hydrochloric acid. And it is mixed with 100 milliliters of 0.1 molar sodium hydroxide. So that's A. We're mixing 100 milliliters of each solution. They're both the same concentration of 0.1 molar. Then in flask B, we've got 100 milliliters, but this time it's 0.2 molar. So we're doing the same reaction. We're asked which flask would have the fastest rate. And in this scenario, it should be flask B. Flask B has the higher concentration. Higher molarity, we just said, means more moles, which means more particles, which means more collisions. So we've just talked about a couple of scenarios, and we're now asked what seems to be an important factor impacting reaction rates. And so in all of these scenarios, we talked about the fact that if we had more particles, we would have more collisions. And more collisions would mean a faster rate. So what we're going to find is going to be an important factor impacting rate is going to be concentration. In fact, we're going to find that concentration will actually be one of the biggest factors impacting our reaction rates. Going back to container 1 and 2, what do you think would happen to the speed of the particles if we increase the temperature of each container? What would happen to their energy? So we've got to remember that temperature is a measure of the kinetic energy of our particles. And that is the energy of motion. So if we increase temperature, that increases the particle energy, which in turn increases our particle motion. And so if our particles have more motion, those particles are going to speed up. So if we've increased temperature, which is speeding up our particles, what do we think is going to happen to our collisions? Are we going to have more or less collisions? What we would find is we're going to have more collisions. Particles move faster, they can collide sooner, they're going to collide more often. And then we're asked in general, what happens to the rate of a reaction as temperature increases? So if we're speeding up reaction rates, or we're speeding up collisions, we're getting collisions faster and more often, we're going to find that our rate increases. So far we've talked about two things that are going to impact rates of reactions. That's going to be the concentration of our particles and the temperature. And both of these are going to have the largest impacts on our reaction rates. Now, looking at another scenario, we've got calcium carbonate, which is a compound found commonly in marble or limestone. Calcium carbonate can react with acids such as hydrochloric or sulfuric acids. If objects such as marble statues come into contact with acid rain, this reaction can lead to them deteriorating or eroding. We find, however, that powdered samples of calcium carbonate in the lab react far faster than a lump that we might find in a statue. Now, with our next scenario, catalytic converters, which are an important component of your vehicle, these things take poisonous compounds such as carbon monoxide and nitrogen monoxide and converts them to less harmful things such as carbon dioxide and nitrogen. This process requires extremely fast reaction rates. To achieve this, so we're trying to get that faster rate, they coat metals such as platinum, palladium, and rhodium in thin layers on a honeycomb structure to maximize surface area. So based on both of these scenarios, we're asked what seems to be another important factor that influences rate. So in scenario A, we have powdered samples reacting quicker than lumps of a sample. In scenario B, we're told we have to create a thin layer to maximize surface area. If I'm comparing a powder to a lump, powder has more surface area, more points of contact. So what we're going to find is that it is going to be surface area that has an impact on rate. So this becomes important if we're talking about reactions of solid materials. Now in scenario 2, the metal is a catalyst. So we said we were going to put the platinum, palladium, and rhodium on that honeycomb structure. We said the purpose was to get those extremely fast rates, and that metal is a catalyst. So that would mean that the purpose of that catalyst is going to be to speed up the reaction. Now we're going to spend a lot of time this semester talking about reactions in solution. And when we have a reaction in solution, solvent choice can play a role in reaction rates. So we're asked, why might this be the case? So we've got to think about talking about our solutions. Remember, to form our solutions, we had to break solute attractions, we had to break solvent attractions, so the particles can get in and amongst one another and become uniform. Well, the strength of those attractions is going to govern how well they dissolve. But remember, if we mix our solutions, we're going to have to break attractions again. So remember, our solutes have to come into contact. Their ability to come into contact is going to depend on how strong the forces are they have to break to come into contact with one another. So when we say that solvent choice can be important, if our solvent is too strongly attracted to the solutes, it can become hard to break those attractions and get our solutes to interact. So we have to choose the right solvent where we have enough attraction to form the solution, but the attraction is not too strong that the solutes can't come into contact. Now with problem 12, we're told that mold and bacteria contain enzymes. Enzymes are biological catalysts. And so these enzymes aid in the spoiling of food. Based on what we've seen in terms of factors that affect rate, why does food spoil quicker at room temperature than if it were stored in the refrigerator? So if we think about room temperature versus refrigerator, we're talking about a temperature difference. We said that higher temperatures were going to result in increased rates. So if we leave that food sitting in room temperature, the higher temperature than the refrigerator, it is going to allow those enzymes to work even faster, causing that food to spoil more quickly. And then finally, based on factors that impact reaction rates, we're asked, why is there a greater danger of explosion in places such as silos or coal mines, where there are larger quantities of powdered combustible materials? So we already talked about in a previous scenario about powdered substances. Powder is going to have large surface area. And greater surface area gives us more points of contact so our particles can collide. It's going to give us the faster rate. So all of these factors we've talked about so far, they're going to be factors that impact the ability of our particles to collide. So we have talked about concentration. We have talked about temperature impacting rate. Surface area. Also related to that surface area can also be impacted by phase. So certain phases can move more easily, so we can get more collisions of our particles. We talked about solvent choice. And catalysts. So these are the primary factors that are going to impact rate. Again, with concentration and temperature being some of the more, or having the greater impacts.